In the previous video, we covered the basic ideas behind qubits, but that in itself isn't very useful. Just like how learning about binary isn't the whole story of classical computing. Rather, what is interesting are the manipulations we can perform upon these qubits. In quantum computing, these are called gates. More formally, they are all unitary operations upon the tensor product of the qubit Hilbert space. There's a plethora of named unitary transforms, such as the usual Pauli X, Y, Z gates, the Hadamard and Toffoli S, and controlled gates, and various universal rotation gates. Some of these can act on 1, 2, or even 3 qubits simultaneously. All of them can be explicitly represented as matrices in the computational basis. As an example, let's apply the X gate to the 0 state. As we know, the Pauli X operator has this form, and the 0 eigenvector is this. Performing the multiplications, we obtain the 1 eigenvector. We have thus found the quantum equivalent of the classical NOT gate, or the bit flip. As another example, let's apply the Hadamard gate. This should be a pretty familiar example, one that we've all seen before. Computing it out, we obtain the plus state, or the up X eigenstate. This, as we remember, is just a basis change. In fact, this basis change becomes very important later on when we start talking about the Quantum Fourier Transform, as we shall see. On a box here, we can imagine it as taking your up 0 state and turning it right onto the equator. Another really important family of gates that we have to consider are the phase shift gates. These have the following action, where phi is some phase. Visually, what we have done is that from an arbitrary starting state on the left, by applying the unitary rotation, or the phase gate, we essentially rotate that vector around the equator, or the z-axis, by some amount of phi. Note that this doesn't actually change the computational outcomes. The probability distribution remains the same. All we have done is just added an undetectable phase onto our quantum state. Note also that the starting vector does not actually have to start on the xy plane. It can start anywhere that you'd like. As a matrix, this has the following form, where you can see that the 0 bit remains unchanged, and we add a phase to the 1 state. One really important idea in quantum computing that you might not have seen before is the idea of controlled operations. Perhaps to us, this may be more familiar as entanglement. One really important instance of this is the CNOT gate, or the controlled NOT, which selectively applies a NOT to the target qubit depending on the state of the control qubit. If the control is 0, then nothing happens. If the control is 1, then it applies an X or NOT operation to the target. It is also called the CX gate. In a quantum circuit, it looks something like this. And as a matrix, it looks like this. You can see how if the control is 0, we have the identity operation, but if the control is 1, we have the NOT operation. We can also apply the CNOT operation to any arbitrary 2-qubit state. In this case, the CNOT operation just simply flips or exchanges the amplitudes on the 1, 0 and 1, 1 states. We can in fact extend this idea of controlling to all such unitary operators. For us, the really important gate is the controlled phase gate. This has a form that looks something like this, where we apply a unitary phase shift by phi on qubit 2, if and only if the qubit 1 is equal to 1. Now let's analyze an example circuit to really try to get the hang of things. So our circuit contains a Hadamard, an X, and a controlled phase rotation gate. Let's start by writing down the first layer of operations, the Hadamard on the X on each qubit separately. The Hadamard turns the first qubit into a plus state, and the X gate turns the second qubit into the 1 state. So at the end of these two operations, we end up with this state vector, where we have combined the two individual states by applying the tensor product. This is the current quantum state after the first layer of operation. Next, we want to apply the controlled phase shift. We can just simply write down the matrix and take the matrix product of the controlled phase gate with the state vector that we obtained above. Since the controlled phase shift gate is diagonal, this is a very easy product, and it gives us this following state vector. This would be the final output from our quantum circuit, but let's say we want to measure it. Measurement is fairly easy. We take the mod square of each amplitude, which then gives us probability distribution. With this fundamental knowledge about how to mod and the controlled phase gate and basic ideas about the quantum circuit, we're actually prepared enough to tackle the quantum Fourier transform, which is what we turn to next.